So you'll notice that the homework I have due next Thursday. I don't think that should be horribly long. I don't think it should take horribly long. A couple of things to think about in there, but like I said, I don't think it'll be horribly long. It'll be like what's the things we've done. We'll derive an open method today. We talked about the ones we've done so far have been closed methods. We'll derive an open method today. We'll talk about what we mean by a composite quadrature rule. And then we're going to get into numeric differentiation today as well. So, like I said, I don't think your homework will take a whole lot of time, that particular one. Major assignment, I think, will take a little bit longer, which is why I have to do after break. All right, so I've got to do the Tuesday after break so that you'll have time to work on it. I don't think it should be too onerous. It might take a little bit of getting used to playing around with GeoGebra to help you solve the systems of equations that are in there. But I think once you start getting into it, I don't think it'll take you horribly long either. Longer than the homework, but not horribly long. Okay. It looks more onerous than it is because there's a lot of words. I know there are a lot of words in there, but some of the words in there are just telling you how to enter the appropriate commands in GeoGebra. So I don't think it'll be terrible. All right. The interesting part for the major assignment is to lead you into quadrature rules that can use fewer nodes to get higher degree equations. So far we've talked about the Newton-Cotes quadrature, which use n nodes. You're guaranteed to get n-1 degree polynomials integrated exactly. You might end up getting n degree polynomials integrating exactly, but you don't get any guarantees for that, and you certainly don't get any guarantees for higher than that. Gaussian quadrature, you get, if you use n nodes, you get polynomials up to the degree 2n-1 integrated exactly. So you get higher degree polynomial precision in your integrals than you do from just using Newton-Cotes. The trade-off is that you have to recompute the nodes every single time when you come up with a new rule. So there's trade-offs between the two. Versus we use equally spaced nodes for Newton-Cotes. Of course, there are issues with Newton-Cotes nodes as well because we said that, we didn't show anything, but we said that eventually you're going to have issues. The more nodes you add, you're going to introduce more errors, especially on the ends, kind of like we saw with the polynomial interpolation. That's essentially what we're doing, is we're interpolating a set of points with a polynomial and making sure that you integrate that polynomial exactly. That's the whole idea behind it. We know that more points don't always help. We've already seen that. Okay. We might go back into more of that in depth later in the semester, but that's why we have to have other methods to help us with the integrals. All right. Any questions on anything at all before we get going? Also, don't forget that your project proposals are due next Thursday. I'll get a Dropbox put in there today, as well as Dropboxes for these assignments. You'll notice at the end of the major assignment, too, I put extra credit opportunity in there at the end. I'll put a separate Dropbox in for that. So if you do not want to do the extra credit or don't feel like doing it or what have you, don't worry about it. Don't put anything in there. If you decide to do it, it'll be in a different box for me to grade. So then it's not all mixed together. Fair enough. All right. Well, let's continue on with our quadrature rules. In particular, I want to finish up with talking about open quadrature rules, what we mean by that. We've already mentioned that a little bit. And then also composite rules, which are the rules that you're kind of familiar with from calculus. Okay. All right. So open quadrature rules. All we mean by an open quadrature rule, and I mentioned this last time. Open quadrature rule just means that you do not include the endpoints as nodes. So your closed, the ones we've been doing, of course, you do include the endpoints. Okay. So to develop an open quadrature rule, we're going to do basically the same stuff that we have been doing. So let's say that as an example, let's develop a let's not do a 3. Let's do a 2-point open quadrature rule. I didn't want to do a 3-point because I'm pretty sure I had that on your homework. Let's see if we can develop a 2-point open quadrature rule for integral from 0 to 1, f of x dx, kind of our default interval. I will mention, just that I meant to mention this when I handed it out. On your major assignment, it changes up the interval. It goes from -1 to 1 for the interval for your quadrature rule, so just pay attention to that when you're doing it. Okay, it'll throw you off if you try to do 0 to 1. Okay. All right, so let's develop a 2-point open quadrature rule for the integral from 0 to 1 of f of x dx, and we'll use equally spaced nodes again. So a little bit different idea here for equally spaced nodes. What do I mean by that when we talk about an open quadrature rule? Well, what I mean is that if we included the endpoints, we would still have equally spaced intervals. Okay? So even though we're only using 2 points, say I have my 0 and my 1 here. If I have my 0 and my 1 there, you're welcome. Then wherever I put my other 2 nodes, I want to make sure that these 3 distances here are all the same. Does that make sense? Okay, all right. So what do those lengths need to be if they're all going to be equally spaced? A third? Good. So what do the coordinates need to be for your nodes then? 1/3 and 2/3. Good. So equally spaced nodes probably isn't the right terminology. I'm just making it match what we've talked about before with closed nodes. What I probably really should say are equally subintervals. That probably makes more sense. That's okay? All right. But again, we're only going to use these 2 nodes to help us figure out what the integral is. We have 2 nodes. So what type of polynomial up to a certain degree are we going to be able to integrate exactly? At least I saw, it's degree 1. Yeah, I saw a couple of fingers go up. But yeah, it's degree 1, right? And again, think about why that's true. We already know the nodes, but what I don't know are the weights, right? But remember, the nodes are what you're plugging into the function. You multiply it by the weight, you add it up, that's what gives you your approximation for your integral. Well, I have 2 unknown weights, so I need 2 equations, right? The only way I'm going to form those 2 equations is if I try to figure out a constant term and an x term. Okay. Or think about it from a polynomial interpolation standpoint. I have 2 points, that's going to determine a linear function. Okay. All right. So our equations that we'll set up are going to be what? What 2 equations do we need to solve in this case? Remember, again, we're trying to find something that looks like, I'm going to write it generally. That's what our general quadrature rule looks like, right? What's your n in this case? 2, right? So we only have 2 terms in our sum, so I'll have a W1 and a W2. And what are the nodes again? 1/3 and 2/3, right? So I'm not trying to figure out what the nodes are. I already know what I'm going to plug into the function, right? So this is the form of our quadrature rule that we want. We need to get 2 equations to be able to solve for the W1 and the W2. And the way we're going to get those equations that we want to integrate linears exactly. So what 2 equations are we going to set up? Or what two integrals do you want to do to help you get the equation set up? What two integrals do we need to do? Yeah, integral. Yep, the integral. Yep, good. Integral from 0 to 1 of dx and x dx. Good. Remember, we're always going to integrate those monomials over the interval. Sorry. That's how we're always going to get the constant on the one side of the equation that we need to solve, no matter what. Okay. So we need to do those integrals. Integral from 0 to 1 of dx is just 1, and for x dx it's what? I'm sorry. That's a half. Yep. Good. One of the reasons why we do from 0 to 1, it makes it a little bit easier, right? It's just going to be 1 over whatever the power, 1 more than the power. So if you integrate x squared, you'll get 1/3. Integrate x cubed, you'll get 1/4, and so on down the line. Makes it a little bit easier to set things up. All right, what does the right-hand side of the equation look like? Well, I know I'm going to have a W1 and a W2 in both. Well, potentially I'll have a W1 and a W2 in both equations. What do we do with the nodes? Where do we plug the nodes in? Where do we plug the nodes in? Say that again. Yeah, it'll be that. Yeah, we're going to plug it into the function, and then that's what we're going to multiply by in the W1 and the W2, right? The nodes go into the function that you're integrating. That's the whole point of the quadrature rule, right? You're going to take the node that you have, you're going to plug it into the function. Again, think about it as, from a geometric standpoint about what you did in Calc 1, when you first introduced definite integral, you used the function as the height of the rectangle, right? But you took the point and you plugged it into the function, right? What you did with Riemann sums back in Calc 1 is a quadrature rule. Your weights were just the length of the subinterval. Your weights were delta x. And your nodes were either usually you did a left endpoint if you did a left sum, or a right endpoint if you did a right sum, or a midpoint if you did a middle, right, if you did a midpoint rule. Right? Okay. All right, so for your first equation, then what are your coefficients on the W1 and the W2 going to be? 1, yeah, because we're just integrating the constant function, right? So I'll write those even in red there, right? What are your coefficients going to be in your second equation? 1/3 and 2/3, good. Because it goes into x, right? If you had an x squared, it'd be 1/3 squared or 2/3 squared. I mean, it wouldn't have an x squared for the 1/3 and the 2/3, but that's what it would be if you were plugging it into x squared. It's okay? All right, and now we just need to solve. So I'll just write it off to the side since I put those in red. W1 plus W2 equals 1. 1/3 W1 plus 2/3 W2 equals a half. Pick your favorite method for solving a 2x2 system. Let's just multiply. I want to multiply the second equation by 3. And then I'll subtract. If I multiply the second equation by 3, you'll get a W1 plus 2W2 equals 3/2. Right? So if I subtract, you should get a W1 equal, or excuse me, a W2 equals a half. If I did my arithmetic right. Right? If I subtract up, take the second minus the first. So it also makes W1 equal to a half. Right? So in this case, your quadrature rule should be approximately equal to, I keep writing equal signs. Your quadrature rule should be 1/2 f of a third plus 1/2 f of 2/3. What questions do you have on that one? Let's use this. Say you wanted to approximate integral for x squared, just to see what it looks like. Using this quadrature rule, what would your approximation be? Well, so where do the 1/3 and the 2/3 go into? The function. So you would have 1/2 times 1/9 plus 4/9. 5/18. Good. That I agree with. Okay. Is that the actual integral for x squared for 0 to 1? No, what should the answer be? 1/3, which is 6/18, so it's not that far off, right? It's not horribly far off. You could do a relative error, I suppose. Take an 18th and divide it by a third, you get a sixth. So I guess it is kind of far off. It's 16.6%. All right, but that's how you would use your quadrature rule to give you an approximation. And again, we could see why it's off, of course. Let's just look at a graph real quick. If you've got your graph of x squared, this is the area we're trying to find, right, under there. But what are we using instead? We took that point and approximated with a line, right? So we've gained some area here, we lost some area here and here, right? Even subtracted some area off down here is the way I've drawn it. I don't know if it actually crossed the x-axis or not, but you can see why it's not going to be exactly right. We've gained some in some spots, we've missed some in other spots. Right? Okay. So it really is an approximation. So we didn't get any extra degree here from this particular rule. But notice the process wasn't any different than what we did before, right? The process is identical with what we did before. Questions on that at all? All right. Let's see if we wanted to extend this to what we refer to as a composite rule. Let's say we wanted to do, let's say using this quadrature rule, let's approximate integral from 0 to 2 of x squared dx with what we'll call a composite rule. Now I'm going to be very specific as to what composite rule I'm going to use for this problem. But in general, remember we also talked about how we can transform our quadrature rule from 0 to 1 to any interval a to b, right? So you might be able to transform it into smaller pieces and then add those pieces together. We'll talk about that here in a few minutes. Okay. Right now, I want to do a very, very simple example. We just came up with a rule from 0 to 1. I want to go from 0 to 2 in a composite fashion. What natural composite do you think I might want to try to do? If I already have a quadrature rule for a length 1 interval, what do you think I might want to do with this integral to help use that quadrature rule the way we wrote it? What do you think we'll probably want to do? 0, 1, and 1 and 2, right? Each of those has a length of 1 interval, right? So let's do that. Okay. When I say a composite rule, there might be many that I'm talking about, right? But right now, I just want to use the rule we came up with for a length 1 interval and see if we can apply it to an integral for a length 2 interval. Does that make sense? Okay. So we'll think about 0 to 2 of x squared dx is 0 to 1 and 1 to 2. Well, the first one we just did a minute ago, but I'm going to write it out longhand again. This one we did, our weights were a half, and the nodes were 1/3 and 2/3. We just did that one a second ago, right? Are the weights going to change when we go from 0 to 1 versus 1 to 2? Or are we going to use the same weights? Same weights. Same, right? We didn't stretch the interval at all, right? All we did was shift. We went from 0 to 1 to 1 to 2. So the weights themselves won't change. Now, if I stretched or shrunk the interval, my weights would change. Okay? Those weights are based on the length 1 interval. Okay. Do the nodes change? Yeah, what should they change to in this particular problem? And how did you come up with those? Say it again. Oh, yeah, so between 1 and 2, and then what did you say about the thirds? Oh, it splits it up into thirds? Okay. So yeah, you just split the nodes into, those two nodes split the interval from 1 to 2 into 2/3. Into thirds, sorry. Is there a way to think about it as a shift? Probably, if I'm asking, right? Yeah, we just add 1 to each of them, right? We just shifted it over 1 unit. So just 1/3 plus a 1 and 2/3 plus a 1. Right? We just literally just did a shift over. Okay. So in this case, we simplify a little bit. I already know that part is 5/18, so we did that simplification a second ago. Oh, oopsie, they're squared, so I forgot squareds on there. This should be 16 over 18 and 25 over 18. Pardon me, goodness. 46 over 18, which is what, 23 over 9? If I did my arithmetic correctly. And of course, the actual value is what? Eight thirds, which is 24 over 9. So a little bit more error in this case, right? Certainly absolute error is twice as big. Which again makes sense because we're trying to, it makes sense that we're getting errors, but it also makes sense that it's not as bad as it would have been if we would have stretched it and only used 2 nodes. We'll do that here in a second. But what did we do? Instead of trying to approximate this with 1 line, I think about what the picture looks like. Oh, it doesn't look like a parabola. We did 2 different lines, right? We did one, now this is a terrible picture. We did one that looks like this. And then we did the same thing again and did one that was like this. Right? And made a couple of sticks to help us approximate. So that's the idea of a composite rule. Literally, take your rule that you have on an interval and just stitch it together. That's what a composite rule is. Sounds fancier than it really is. If we would have just used the one quadrature rule and not the composite rule, let's say we wanted to do this with just by scaling the original rule. So using the one rule, not the same rule twice stitched together, but using the one rule that we came up with, what's going to be your weights and what are going to be your nodes? We talked about scaling last time. Say it again. Okay, I agree that your nodes are going to be 2 over 3 and 4 over 3 because your interval's is twice as long, right? It got stretched, right? How about your weights? Which is 1. Why is it 1? 2 minus 0 over 2 is 1. Exactly right. Remember, that was b minus a over whatever, b minus a times whatever the weight was to start with, right? Your weights in this case were a half. Your b minus a is 2, right? So we're just going to get a 2 times, I'll just write it this way, a 2 times a 1/2. So in this case, we would have, for this particular problem, you would have 4/9 plus 16/9, which is 20 over 9, which is worse, which makes sense that it's worse, right? Because now if you think about your picture, again, you're only trying to use the one line, which makes it even worse, right? So that's why we like the composite rules. It means that we don't have to scale things as much. We might have to do more computations. There are certainly more computations involved in trying to slice up your interval into smaller pieces and use your quadrature rule than using a single quadrature rule, right? Okay, but slicing things up into smaller pieces gets you better accuracy. Like everything else we've talked about this semester so far, there's a trade-off, right? Every time you do more computations, you also might run the risk of losing accuracy as well. So there's always going to be inherent errors in doing your computations with rounding or whatever happens that way. And then there's inherent errors in using not enough pieces of information from the approximation error. So you got approximation errors and you've got rounding errors. So you got to worry about both of those things. And we actually, it's been a while, but we actually demonstrated that, right? We said we added more, we got smaller and smaller step sizes and our error went down, and then all of a sudden it went back up again because we got into the rounding errors as we got too small. So you're looking for a sweet spot, if you will. As you get more and more into applications, especially computational applications, you find a lot of it is more artistry than it is exactness, exact math things. Just trying to piece together things that give you the best answers. All right. Questions on that at all? Okay. Let's talk a little bit then about what the composite rules look like for rules that we've already talked about. So when you've got something like composite trapezoidal rule, say, Well, remember our trapezoidal rule from 0 to 1 looked like what? Good. Yep, 1/2 f of 0 plus 1/2 f of 1. Good. Okay. Now, think about if we scale it to any interval from A to B. What's that going to look like if I scale it from an interval from A to B? Yeah. F of good. Yep. And a b minus a over 2 f of b. It's exactly right. Yep. And it doesn't matter what the a is or what the b is, right? The length of the interval gets scaled, and then we plug in the endpoints, right? Okay. So let's think about it in another way. What if I did it as integral from a to an a plus, say, some delta x of f of x dx? What's your b minus a in that case? Yeah, a plus delta x minus a, which just gives you delta x, right? So you'd have delta x over 2 f of a and a delta x over 2 f of a plus delta x. That'd be the next one over, right? We'll write it that way. I'm getting somewhere, I promise. This literally is just scaling the one piece of the trapezoidal rule to some other interval, right? Now let's introduce a composite, okay? The composite that I want to do in this case is I want to go from a to a plus 2 delta x. Why do you think I wanted to introduce this one first? How do you think I might want to split this integral up? Compare it to what we did with the previous composite rule that we did in our example. What do you think I might want to do here? How do you think I might want to split this integral? Let's think about the previous example. We had the integral from 0 to 2. You told me to split it how? Because we had a quadrature rule for from 0 to 1, right? We had a quadrature rule for that length 1 interval. Looking above, we have a quadrature rule for a length delta x interval, don't we? So how do you think we might want to split this into 2? Good. Yeah, exactly right. Let's go from a to a plus delta x, and then a plus delta x to a plus 2 delta x, because each of those has length what? Delta x, right? Each of those has a length of delta x, doesn't it? So let's put these two pieces together. The first one obviously is just, well, hopefully it's obvious. It's going to be just the rule we came up with in the previous line. So we should have delta x over 2 f of a plus delta x. Is there any scaling that we need to do for the second one? No. So it's still a delta x over 2. Why do we not need to do any scaling? Did we change the length of the interval from one to the next? No. We only have to change the scaling if we change the length of the interval, right? That was why we split it where we did, because it keeps the same length. However, we do need to change our nodes. What are your new nodes? Good. And then notice I've got two of the same term, don't I? Yep. So when I add those together, we get delta x over 2 f of a plus 2 f of a plus delta x plus f of a plus 2 delta x. Let's think about the picture for just a second, and then we'll see if we can extend this a little bit and see if it matches what you remember from Calc 1 or Calc 2, depending on where you learned it. Okay? We've got function, whatever that function happens to be. We've got an a, we've got an a plus delta x, we've got a plus 2 delta x, point. I don't know why when I draw these things, everything's always looks like a straight line across. I'll try to make this look a little bit better. We've got that as the top of one trapezoid. And we've got that as the top of another trapezoid. Notice that this height right here gets used twice, right? Which is where that 2 comes from in there. That's the argument you make in Calc 1 or Calc 2, right? You've got butted up trapezoids, right? All right. So if you did something like, let's say we had a to a plus 3 delta x, what do you think your quadrature rule is going to look like? This should be approximately equal to up here, by the way. Those are definitely not equal to each other. What do you think your quadrature rule is going to look like here? Good. Okay, let's think about where these came from. I've got those two match for one of the quadrature rule, or sorry, one of the intervals, right? That would be the one from a to a plus delta x. Then you've got one from, I'll write that down, a to a plus delta x. This is a plus delta x to a plus 2 delta x. And this one goes a plus 2 delta x to a plus 3 delta x. And we see the overlap, right? We've combined like terms, but we see that overlap. Notice that there wasn't any geometry really here, right? Think about how we motivated our quadrature rules. Our quadrature rules were not motivated by geometry like they were in calc, right? Our quadrature rule was, I want to come up with a rule that integrates linear polynomials exactly over the interval. And technically I should say, I want to come up with a rule that integrates linear functions over the interval exactly using a closed quadrature rule to use the endpoints, right? That was how we got the trapezoidal rule. And it matched what we got in calc, which is good. Otherwise, everything that we learned so far will be garbage. These things should match up, right? Okay. But notice we didn't. I confirmed it, if you will, with the geometry, even with my terrible drawing. But that's not what our motivation was. Our motivation was all about I created this rule by saying I want to integrate this specific class of functions exactly. Here's what the rule is. Now I've stitched the rule together several times, and oh hey, look, it looks familiar to what we did in calculus. Right? And of course you could extend this. For Simpson's rule, of course, it would look similar, right? Remember Simpson's rule when you wrote it with delta x, you did your interval that you really did was 2 delta x long, wasn't it? So let's see if we can put together our composite delta x, or composite delta x, our composite Simpson's rule, or technically our composite Simpson's 1/3 rule, because now we have 2 Simpson's rules, right? We got one Simpson's 1/3 and Simpson's 3/8. All right, so remember what Simpson's rule looked like from 0 to 1? One-sixth f of 0. Good. This was Simpson's 1/3 rule. Let's do the same thing, but I want to try to make it match what we did in Calc 1, okay? Or Calc 2, sorry, not Calc 1. Unless you had an advanced Calc 1 class. So unlike what I did for the trapezoidal rule, let's go from a to a plus 2 delta x and apply the quadrature rule that we just had. Okay, and then hopefully we'll see why it's called Simpson's 1/3 rule here in a second. What do we need to scale our weights by? What quantity do we need to scale the weights by in this case? That's a 2 delta x, right? Because that's the length of the interval. When I go through by the 2 delta x, we'll get delta x over 3, right? F of 0 plus 4 delta x over 3 f of, not f of 0, f of a, because it shifts to a, right? What's the middle point going to be? Yep, and so in this case it's, yeah, it's okay. It's the, yeah, a plus the delta x, yeah, it's halfway there, right? And then the next one's going to be delta x over 3 f of a plus 2 delta x, right? Do split into 3 pieces in this case, or 3 nodes, to get those equally spaced intervals, equally sized intervals, equally spaced nodes. And now notice that you can factor out a delta x over 3, and you get f of a plus 4 f of a plus delta x plus f of a plus 2 delta x. Now do you see the 1/3? Yeah. Notice that we made this be a 2 delta x length interval in this case, because remember again, for Simpson's rule, we need 3 nodes, and we typically think of the spacing between nodes as our delta x, right? So that was why we went an interval of 2 delta x, so that we had left endpoint, move over 1 delta x to get the midpoint, move over another delta x to get the right endpoint. Okay? So if you did something like, oops, let's do another one. kind of build this up again. Say I do a plus 4 delta x and make a composite. Well, our first piece, and again, notice I made this twice as long, right? So I'm going to break it up into 2 pieces for a composite rule. So the first piece will be exactly what we had. What will the next piece look like? Do we need to change the scaling? If I break it up at the 2 delta x spot, do I need to change the scaling at all? Nope. So we'll still have a delta x over 3 in the next piece. Oh, hey, that was fun. But we do need to change where the nodes are, right? What are the 3 nodes in this case? If we go from a plus 2 delta x to a plus 4 delta x, what are the 3 nodes? Okay. Good. Good. So again, here's our quadrature rule for that one interval from a to a plus 2 delta x, transformed from our quadrature rule from 0 to 1, right? Here's our quadrature rule from a plus 2 delta x to a plus 4 delta x, again transformed from 0 to 1. But since we use the same length interval, I didn't have to change my weights, so I still have a delta x over 3 out in front. I can pull it out again, and do you see any like terms that you can combine? Should get a laser pointer, so I don't have to walk over there. I'm lazy. Mathematicians are inherently lazy. So, do you see any like terms we can combine? Yeah, these two, right? It's that overlap point again, right? Oops. So we've got delta x over 3 times f of a plus 4 f of a plus delta x plus 2 f of a plus 2 delta x, and then a 4 f of a plus 3 delta x, and finally an f of a plus 4 delta x. Does that pattern look familiar to you when you learn Simpson's rule? Yeah, it should. And again, it's nice that it matches, right? Because think about where Simpson's rule came from in Calc 2. You really did the exact same thing, but you didn't really think about it as polynomial interpolation. You're like, I'm going to take 3 points and I'm going to put a parabola through it. And then I'm going to find the area under the parabola. So then you do all that integration and make everything. And it's like, oh, well, if you really derived it, you were probably fancy of, well, let's start it at 0 and go from minus h to h. And then all these numbers come out a lot nicer. But you stitch together parabolas, an area under parabolas, and put them together. And again, here, similar, but we really didn't motivate it from the geometry, right? We just said, I want to integrate this type of function exactly. I want to integrate quadratics exactly. Here's what the coefficients have to be if I use equally spaced nodes. And oh, look, it matched what we got for Simpson's rule. And then again, you could stitch together another one, go to a plus 6 delta x or a plus 8 delta x and keep going. And keeping that delta x interval way through. Notice this did require even number of subintervals, right? When you did this in Calc 2, you'd have an even number of subintervals to be able to do it. Because you need 3 points to get a parabola, and then you share that one in the middle each time. So you need an odd number of points or an even number of intervals. Pardon me. This idea of composite rules starting to make sense, I hope. Okay. All right, so that pretty much talks about what I want to do for numeric integration for right now. All right, you've got your homework is on this quadrant. I'm going to start new stuff here in a second if I can stop coughing. You've got homework over basically what looks like this stuff, all right, that I just gave you. And then your major assignment is to investigate what happens if you want to do a similar concept, but not specify what the nodes are to start with. Can you find special nodes that allow you more degrees, if you will, of polynomial accuracy for integrals? So not only do you just find the weights, but you find the weights and the nodes. Okay. So that's the idea. All right, well, I'll say switch gears, but really we're just going to put it in reverse. Rather than doing numeric integration, let's talk about numeric differentiation. Okay. In your textbook, when they start introducing this stuff, they talk about a lot of physical world representations that involve derivatives. And if you're going to be doing anything that talks about how things change, it's always going to be involving a derivative. So if you're going to be solving differential equations or any of those kinds of things, you need to be able to know, how to deal with those things numerically. Because most things that pop up in a physical sense, you're just not going to be able to compute by hand or find an exact answer to. You're going to have to use numeric approximation techniques to get at it. Okay. So let's start with your most basic numeric differentiation formula that you learned back in Calc 1. So remember that if, let's say we have y equals f of x, and we want to find the slope of the tangent line, I'll say x equal to x naught. This is where you started Calc 1, essentially, right? And just to remind from Calc 1 concepts why this is a hard idea in general, I'm asking you to find a slope of a line. What do you typically need to know for a slope of a line? How many points do you need? 2, right? But if I'm doing a tangent line, I'll only give you 1, right? This is why it's a hard problem, right? It's certainly not a pre-calculus problem, right? Pre-calculus, you need 2 points, and I'm going to find the slope of the line between those two things, right? So that's why it's a hard problem. So the way you started getting at it was, okay, well, I'm going to start trying to make it a little bit more rigorous the idea of I'm going to take these 2 points that are really, really close together, right? So we did it with a limiting idea, right? That was where limits came from, which is why you start calculus with limits, because you need limits to talk about derivatives. And that was the whole motivation for trying to do calculus in the first place, is to find a derivative, okay? Find the slope of the tangent line. All right, so you had to make rigorous this idea of, I want to take points that get smaller and smaller and smaller and get closer and closer, or not smaller and smaller. I want to take these points that get closer and closer to the point that I'm interested in, because again, I need 2 points to be able to calculate a slope, right? One way that you did that was, okay, I'm going to start at this point, and I'm going to add a little bit, and then I'm going to make that little bit that I add get smaller and smaller, right? So one of the ways that we did an approximation for a derivative was to, let's say it's at the point x naught. I took the point x naught, I added a little bit. I took the y value at the point that I was interested in. So I calculated the 2 y values, did the difference, and then I divided by how far I went. That's the difference of the x coordinates. I calculated a slope of a line, right? I've got 2 points on the function. I connected the dots with a line, and I calculated the slope, right? Just to give this a name, because we're going to have other names as well, this is what's called the forward difference formula for a derivative. We will have other ones as well. But what I'm interested in is how accurate is this difference, or excuse me, is this formula? So we're going to talk about what we mean by how accurate is this formula. We're going to talk about how we can create other formulas that might be more accurate. Or we're also going to talk about how can I use the same formula but make it more accurate by doing some a little bit of extra work. And we'll talk about what that extra work means a little bit. Probably on Tuesday, but we'll talk about what that extra work means. All right. So the way we're going to talk about the accuracy of this formula here in a second. It's going to require us to remember some stuff about power series. I'm sorry. Okay. All right. But let's talk about how accurate this is, and then we'll talk about the trade-off between finding more complicated formulas that are more accurate, or use the same formula and have a process that can refine it to make this one more accurate, or a given formula more accurate. I should just say for differentiation. So that's our goal, probably going into spring break. Okay. All right. So let's talk about how accurate this formula is. I need to remind you, or maybe tell you, what a power series looks like. Okay. So when we refer to this as a Taylor series, centered at x equal to a. The best way to think about what a Taylor series is think about it as an infinitely long polynomial. All right. So here's what I mean. All right. So the way that we create a power series is that I want to make whatever function I'm given and a polynomial approximation to it match at every level that I can possibly make it match at. And so what I mean by that is I want to make the function values agree. I want to make the first derivatives agree. I want to take the second derivatives agree. Third, fourth, fifth, sixth, seventh, and keep going. That's what we do for making it with this power series, kind of an infinitely long polynomial. That's what we want to do. That's how we make a power series. Okay. Well, if I want to make the function values agree, I'm going to set the first part equal to f of a. That's going to make the constant match, essentially, right? If I plug in a on the left-hand side, I want to get the same thing as when I plug in a on the right-hand side. Okay. If I'm going to make the first derivatives agree, here's what I'm going to do. And let's talk about why these agree. I'm going to make the next term in my polynomial be an f prime of a times an x minus a. Now, why didn't I just use an x? Well, remember, I've already made it to where if I plug in a on the left-hand side, I get the same thing on the right-hand side. I don't want to add anything else to it, right? So if I'm going to add powers of x, I better really add powers of x minus a, so that when I plug in a in there, I get a 0, right? Now look what happens when you take the derivative. If I differentiate this, that's a constant, that goes away. If I differentiate this, that's a linear, that goes away. I'm just left with f prime of a, and now my derivatives match, right? If I stop here, that's your tangent line approximation. That is the tangent line, isn't it? You see it? Okay. Now let's make the second derivatives match. Well, the way we're going to make the second derivatives match is, well, I'm going to put in the second derivative at a. I'm also going to put in x minus a squared, because again, I'm thinking about building up a polynomial. Now I'm missing a piece. Let's think about what the pieces I'm missing. When I differentiate this x minus a squared, what's going to happen with this 2? It's going to come down in front, right? If I want to make sure that things are equal, I'm going to need to divide by that 2. And now you can check that the second derivatives match. Notice if I plug in a, I get f of a. If I take the derivative and then plug in a, I'll get f prime of a. If I take the second derivative and plug in a, I'll get f double prime of a. It works. Okay. Now let's think about the next one. I want the third derivatives to match. So I'll have an x minus a cubed in there. I'll have a third derivative at a, but now I need to adjust my constant. Think about when I differentiate x minus a cubed, I differentiate one time, a 3 comes down in front. I differentiate a second time, a 2 also comes down in front, right? So I get a 3 times a 2. And then if you want to be really pedantic about it, if I still have a first power up there, I bring the first power down in front as well. So I get a 3 times a 2 times a 1. I see a factorial, right? So I get a 3 factorial I need to cancel out. And then this continues. Plus dot, 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 plus nth derivative at a over n factorial, x minus a to the nth, and so on down the line. It looks hard, but the idea is pretty straightforward. I'm not going to say simple, because it's not a simple idea by any stretch of the imagination. But it's straightforward. We're making the function values match. We're trying to make a polynomial on the right-hand side. That's the fundamental idea. Because polynomials are things that we can handle, right? All you do with a polynomial is add backwards, add fast, and add fast, backwards fast. Add, subtract, multiply, divide. Literally all you do is add, right? Just depends on which direction and how fast. Okay? I borrowed that from Dr. Rolf. Okay? All right. So it really is a simple idea. I'm trying to take a building, it's a simple idea, but it's not simple, right? I'm trying to take a fundamental building block of algebra, a polynomial, and make it match some other function that's not a polynomial. That's the idea. Okay? Cool. All right. So that's where we come from. Most of the time, of course, we're using these things as approximations, so we chop it somewhere. And this is where this comes in with our numeric derivative approximation. Okay? All right. So let's go back up to this formula I just came up with. All right? But in particular, I want to look at that piece to start with. Okay? F of x naught plus h. I want to use the power series centered at x naught. Okay? So I'll have f of x naught. Because my a is just my x naught here. Okay? Plus f prime of x naught times, well, let's see what we're doing here. I said my center was x naught, so that's my a, right? What's my x been replaced with? My x here has been replaced with that, right? Right? My x has been replaced with that. So I'll have x naught plus h here, right? And then we'll have f double prime of x naught over 2 factorial. I'm going to write my factorials there because otherwise I'll forget it later. X naught plus h minus x naught squared. I'll write one more, and then I'm going to write dot, dot, dot. H cubed. All right. Inside the parentheses, what does everything inside the parentheses simplify to in each set of parentheses that we have? Just an h, right? So this is equal to f of x naught plus f prime of x naught h plus f double prime of x naught over 2 factorial h squared, f triple prime of x naught over 3 factorial h cubed, and so on. Just writing it on the board so I can refer back to it again. Okay, so I don't have to scroll back up. That was where we started, right? We're trying to get an approximation to the derivative. So what I really want to do is get something that involves just this by itself, right? Okay. So I'm going to solve for it. Well, in order to be able to solve for it, I need to subtract all of this mess to the other side and then divide by the h, right? You see it? If I want to solve for f prime of x naught, everything else needs to move to the right, excuse me, the left. It's right to me is pointing this way. Everything needs to move to the left, and then I need to divide the h out. Okay? So to write that down, we've got f prime of x naught equals f of x naught plus h minus f of x naught all over h. And then there's a bunch of minuses here. Minus f double prime of x naught over 2 factorial times an h, because we divided one out, right? So it's just a single h, minus an f triple prime of x naught over 3 factorial h squared, minus, minus, minus. Without going into a bunch of details, that actually is an equal sign, provided your function is nice in an interval around x naught that we haven't moved too far away from. Okay. At least I don't want to get into the details. All right. Okay. But what do we have? This is the formula right here. This is your formula for basically your formula from Calc 1, right? Without a limit symbol. Okay, so if we chop that off, or sorry, use that for our approximation, this is the part that gets chopped off, right? This part on the end literally gets chopped. We ignore it, right? So we're referring to that as a truncation error. We typically write this in the following manner. We use big O notation. So let me just talk a little bit about what big O notation means in our context. You may be familiar from big O notation in a discrete math class or a computer science class like algorithms or pretty much any other computer science class where you talk about algorithms. Usually you look at your big O notation as what you look for the highest power because you're doing an integer number of steps of something. Is h big or is h small here? Small, right? Higher and higher powers of really small numbers get even smaller and smaller, correct? So the error here is dominated by the lowest power of h, not the highest. Okay? So that's why we write O of h. This is what we refer to as the truncation error. Whoops, that was weird. Truncation error. Really, you can really nail this down with more theory. There's something referred to as Taylor's theorem that says that the piece that's left over on the end for a power series really does depend on the first term that you drop off. I mean, you can actually, it's an extended form of the mean value theorem. I'll leave it at that. Okay, that's what Taylor's theorem is. It's really just an extended mean value theorem. But anyway, this is your truncation error. So this is on the order of h. So, great. What does that mean for us? So, basically, this says that the smaller and smaller that you make your h, your error should go down in basically a linear fashion. Okay? It should go down by the same amount each time, if you will. So, for example, if you have the h, then your error should go down by half of what it was to start with. If you quarter it, it should go down roughly by a quarter, and so on down the line. Okay, you should see a linear relationship there-ish. I mean, there's constant multiples of things. That's why it says O of H, not just an H. Okay. All right. So anyway, what we're going to talk about is what other methods might we do to make this better? What I mean by that is, well, what if it was O of H squared? Is O of H squared better than O of H? Yeah, because H squared would be smaller for small h's, right? So if I can make it O of H squared, we should be able to get away with taking bigger h's and still get as good approximations, which from a computational standpoint would be better because we know what? If we start doing things that are really, really, really tiny and get around machine epsilon, things can go crazy, right? So if I can make this at h squared or h cubed or so on down the line, we should be able to get better approximations without having to make my h super tiny, right? I think it could cause issues here, right? We're dividing by it in particular, okay? So that's what we're going to go towards on Tuesday, is try to play around with other types of formulas and see what their truncation errors look like and how we can make those truncation errors better. We're going to have two big methods for doing that. One's going to be playing around with these power series. So make sure that you're okay with seeing the power series in this form here, because we're going to play around with this a lot on Tuesday. And then we'll have another thing that's referred to as Richardson extrapolation, which allows us to improve those error methods without having to come up with new formulas, basically. Okay? So we'll talk about that on Tuesday. Have a good one.